Judges, are you guys ready to go? Awesome. Okay, ready, Team Coco?
Yes.
All right, 3, 2, 1, go for it.
Hello, I'm Adam Brent, the founder of Coco. I'm here today to show you how Coco can help solve the problem of toxic algal blooms, what a tough thing to say, while revolutionizing our agricultural production system, conservation, and so much more. The best part of all of this is that this is nature's own solution with just a little bit of Coco's assistance. Do I arrow? There we go. As you can see, nitrogen and phosphorus nutrients continue to enter the watersheds unabated. The nutrient runoff solution has to work for farmers, taxpayers, and the environment. And the best part is that Coco's solution works for all of them. Coco's solution starts by planting tall grass. Coco's solution starts by planting tall grass prairie buffer strips on every field's headlands. Prairie grass buffer strips sink their roots 15 feet into the soil and trap nutrients and sediment runoff while creating a diverse wildlife biohabitat. Next, we harvest the biomass and we transport it to our compost facility where we compost it with manure and food waste. Finally, we return those nutrients to the fields in the form of Coco high-quality humus compost, which creates a perfect circle. As you can see, when a farmer plants a buffer strip, he loses income and he loses grain production, which is one of the major reasons why farmers don't plant buffer strips unless they receive annual government subsidies. Coco's solution, we think farmers will happily adopt the solution because it produces more food, more income, and more environmental benefits while planting fewer acres. And the best part of all is that it can be implemented on every field. Coco's proprietary composting system works like this. We get paid to take and harvest the biomass as well as the food waste and the manure. And then we compost it and turn it into high-quality humus compost, which we sell back to farmers. Wait a second, you're probably thinking, why on earth would a farmer buy back his own grass? And that's because grass by itself is worthless until it's composted, and then it turns into black gold. The Coco's composting process kills pathogens, breaks down pesticides and antibiotics, and stabilizes valuable nutrients. Equally important, Coco compost contains a proprietary blend of microorganisms which, when they're applied to the field, help suppress soil diseases, which as a result helps lower pesticide applications. Coco can build a facility anywhere that has three things: people, waste, and farms. So while this rules out Antarctica, just about everywhere else is fair game. A single facility will cost approximately $4 million to build, and that includes the planting of the buffer strip costs, and it will generate about $800,000 a year in profits. More importantly though, a single facility can permanently mitigate the nutrient runoff from over 100,000 acres of farmland. Buffer strips have already been proven to do all of these things. We harvest the biomass after the nature has had its fill. Once again, Coco is just composting the leftovers. Coco will create jobs, reduce landfill waste, and manure greenhouse gas emissions. When farmers add our compost to their fields, they immediately improve their soil, which leads to lower fertilizer applications, greater water holding capacity, increased crop yields, and carbon sequestration. We are an experienced team of composters, farmers, engineers, and environmental advocates who started our first facility in Holland, Michigan. Since 2015, we have composted over 18,000 tons of waste and successfully integrated compost into conventional fertility programs. Every farmer could immediately reduce the flow of water off of fields, trap and recycle nutrients, provide a diverse wildlife habitat, and sequester millions of tons of carbon into the soil every year by adopting Coco's prairie grass buffer strip composting program.
Unfortunately, that's all the time we have.
Thank you very much. I had a good practice that.
Excellent. All right, we now have time for 3 minutes of Q&A from the judges. Starting now. Judges, any questions or comments for Team Coco?
Adam, can you define facility for me again? Because I was kind of lost on the numbers there.
I'm sorry.
Define facility.
Oh, so compost facility?
No. Facility as it related to, is that what you meant then by the revenue? The compost
Yeah, so the
facility?
compost facility is effectively a composting operation that's located centrally in say, a given county. And then it's a composting pad with compost turning equipment, heavy loaders, trucks, things like that can process the biomass and manures and food waste and then transform it into the compost, which we then can bring back out onto the field and spread with spreaders.
Then the buffer strip relates to just the requirement of the agricultural facility?
Yes, because of the cost of transport, and you can't make compost. So making compost is it's a chemical component of carbon and nitrogen ratios of 35 parts carbon to 1 part nitrogen. So grass biomass has a lot of carbon and very little nitrogen. Manure and food waste has a lot of nitrogen but very little carbon. So by combining those two elements together in the right proportion and timing, you can create this high-value compost product that then can be reapplied very easily on the field. So you can't really spread grass on the field, but compost is very much like a dirt-like material that spreads quite easily and has the nutrients. But more specifically, it has specific microbes that are responsible for all of soil's functions.
Other questions for Team Coco?
What would you do with the award money?
So we've already been talking about building a facility in the area. So we've met with some of the area's drain commissioners who are very excited about it because the buffer strips help to reduce the sediments flowing into the ditches, which they ultimately have to pay to clean out. So there's a myriad of benefits that would apply to all of these individuals. So right now we're looking at building a facility here in Monroe County.
Time for one more quick question.
Hi, what is the exact role of compost in buffer strip? Like, would it going to change the size of the buffer strip, or like width, or it's just a...
No, so what happens is that the buffer strip provides the ability to make the compost. And since you can't make compost with just manure, and you can't make compost with just food. But if you combine those with the grass biomass, now what you've done is the nutrients that have been absorbed by the buffer strip are pulled up into the plant itself, and then by composting or harvesting and composting those nutrients, you're redistributing them from the edge of the field back throughout the rest of the field.
Fantastic. That's all the time we have for Q&As and for Team Coco.
Thank you very much.
All right, next up we have the microplastics team. Sure. Yes, the first two. All right, judges, are you guys ready?
Yes.
Awesome. Microplastics, you guys ready?
Yeah.
All right, I'm gonna count you down. 3, 2, 1, go for it.
Good afternoon, guys. I'm Chandani and she's Gui, and we are here to present you a project on detecting microplastics in freshwater bodies. So there are two kinds of microplastics that are present. One that are actually manufactured at micro scale, the beads that you find in your toothpaste or the beads that you find in a lot of face scrubs. And then the other kind of microplastics are the ones that degrade. So if you have a lot of waste plastic material in water, because of UV and all the abrasion processes, they degrade and come down to a microplastic level. And the usual diameter that's considered to be considered under the microplastic bracket would be anything that's less than 5 millimeter in size. Now, the issue with Lake Erie is, apart from the toxicology, there's a major issue when it comes down to microplastics. And this is a simulation that shows the amount of microplastic that moves along the water current throughout the year. The device that we are using works on a simple centrifugal force. So with the help of centrifugal force, we are trying to push forward we take a water sample, and based on the size and the density of the microplastics, we are trying to divide and segregate each of the microplastics. So this is a device, and this is actually taken, it's inspired from the diagnostic devices that are used in biomedical industry, mostly for diagnosing various blood samples. So we thought that microplastics are pretty similar to the blood molecules, the molecules that are found in a blood sample, a little bit bigger. So we actually increased the size based on that. And so as you can see, the center, so a sample of water would be added to the center inlet, and then the center, the disc will be put on a spinner. It can be any kind of a motor or anything that spins. And as it spins, because of the forces that are used in centrifugal force, the smaller particles will move forward to the outer edge of the ring, whereas the heavier particles will remain in the center. And this is how we are going to segregate the different kinds of microplastics. And that is the first part of the microplastic segregation. The second part is we want to characterize each of the microplastics that are present, because in order to study the impact of microplastic in the environment, we need to know the various molecular bonds and how they can actually be filtered. Since they are very small in size, using the present filtration process, it's going to be quite difficult. And Raman spectroscopy is going, with the use of Raman spectroscopy, we are going to look at the molecular bonds, and based on the molecular bonds, we are going to find these spectrums. These are the spectrum graphs that are present. The issue that is there right now is all the spectrum graphs that we get for each of the microplastics are based out of like the perfect size of a microplastic. They don't have any abrasions, so we don't have much knowledge that's required. The working process would be, first we take the sample collector, and we use the water in the spinning device, and once the device spins for probably like less than a minute, there'd be a segregation of the sample. And once that happens, we are going to take a Raman spectroscopy microscope, and we are going to take out the data of each and every single microplastic molecules that are there in the water. So our ultimate goal here is this is just like a starting step for collecting data about the kind of beads and the kind of fragments that are there, because while I was actually testing out few water samples, I realized that sometimes it's difficult to segregate between, there might be filaments of like biological filaments, like filaments from an aquatic animal, and that's often mistaken as a microplastic, or sometimes a microplastic also has,
Unfortunately, that's all that's time
Okay.
for the presentation.
all right.
My apologies for cutting you off there.
Yeah.
You have 3 minutes for judges' question and answers with the microplastics team. Judges, take it away. Any questions or comments?
Question. In terms of the issue of microplastic in Lake Erie, so your solution, where does it stand in terms of providing a solution? You're at the science level or you're at the actual policy level? Or
We are at the science level right now because, like I said, what our device basically does is it helps in collecting data. It gives you a very appropriate, the exact amount, and it gives you the chemical properties that are present. It just gives you a full detail about it.
Other questions?
Going about the sample collection process and knowing like the stratification of where the microplastic could exist within the water body?
So we have only done like one sample process so far because it took a while for us to actually design the disc right now. Our next step is to collect all the samples and start. So there's a method in which each of the microplastics are named. It's a standardized method. So based on that method, we are going to make a library of the various microplastics that are going to be present.
Great. We have time for questions.
Why are you interested in this? What's your background?
Both of us are electrical engineers, and what we are interested in is when we were working on the Raman spectroscopy microscope, we realized that mostly that tool is used for detecting various kind of polymers. It can be plastics, it can be other kinds of polymers, but when it came to microplastics, there was very little information and the library was very limited. So we are trying to expand that and give like a more in-depth data for other people to study about.
One quick question.
Yeah.
Anyone? Jennifer? Okay, great. Thank you very much, microplastics. Next up is Windsor, is that correct, Laura? Yeah. Great. Judges, are we ready? Okay. You and Cam, are you ready?
Yes.
Awesome. 3, 2, 1, take it away.
Hello, everybody. My name is David Dewar. I'm a PhD student at the University of Windsor in the Department of Chemistry and Biochemistry. And what I am working on is a strategy for the removal and recovery of nutrients from agricultural wastewater. So generally, the reason we want to do this is to prevent the accumulation and loading of these nutrients into Lake Erie before they cause algal blooms. So let's talk about why that happens first. So phosphate is important biologically. It's used in many aspects, and for that reason, it's put into fertilizer. What also happens is that runoff and accumulation into Lake Erie then results in the formation of harmful algal blooms. These blooms produce toxins that are dangerous to both human and aquatic life. And then this is our solution to combat that. So this is an aluminum framed filter placed into a cement culvert. The way that it works is that the cement culvert is filled with water and the water flows radially inwards. It is removed from the center chamber, and then we have 2 different outer chambers. The first one, chamber 1, is filled with lime rock chips. Now this removes a decent amount of nutrients and quite a bit of suspended solids. The second part, chamber 2, is filled with a high capacity phosphate binder, and I'm going to continue talking about that next. So what we are using is tomato plant roots from a greenhouse, and they have a really large phosphate binding capacity of 55 grams of phosphate per kilogram of root material. And the way that we think they function is like this. They are like a straw. Water flows through the center of the root. While that's occurring, phosphate ions are also flowing through, but they are retained on the interior of the root wall. What we can do after, and the binding affinity is 23.1 millimolar. The best way to think about this number is like golf. The lower the better. This number is approximately 6 times lower than the binding material we were using before. After that, the other key component in our system is carboxymethylcellulose, or CMC. It is a derivative of cotton fiber, and it's used in numerous grades, including food, toothpaste, and detergent. Anyone who has had coffee with 3 minutes a day, you've already eaten it. And what we do with that is solubilize it. We then run it through the root material. This causes a displacement of the phosphate, which we can collect for later reuse. After that, it has one other interesting property. You can precipitate phosphate as calcium phosphate, and when you add CMC to the mix, you require less calcium to produce the same amount of calcium phosphate. And this is just an example of that in the lab. That white powder in the bottom there is calcium phosphate. As we move across, we are getting more and more. And finally, we have done some on-site testing, so we've actually run this in the field. In red, we have the pre-filtration phosphate levels. In green, we have the post-filtration phosphate levels, and we're removing 71% of soluble phosphate using this filter system. Everything I was just talking about has actually already been published last month in the Journal of Environmental Management. And moving on, I now want to talk about what we're going to be doing for Lake Erie specifically. So we are working with the Essex Region Conservation Authority, or ERCA, in the Lebo Creek wetland, so they've built an artificial wetland. This is a picture of the site, and way back there in the corner, which I couldn't get to on that day, there are 3 filters set up in parallel. These filters are going to allow us to test different binding materials at the same time under the same conditions. And what we are planning on testing is 1, plant roots again, 2nd, chemically modified sawdust, and 3rd is cast iron borings from local recycled metal. Now, 3 other things we are interested in working on are the compression of these root materials into blocks or pellets. Now, the only reason we want to do this is to better utilize the space in our filters to allow us to pick up more phosphate before they're full. And the other one is that we want to pack them into these drainage socks. Now, this is good for one major reason. It allows us to set up and tear down a site significantly more quickly. I'm busy, I have a lot of things to do, and I pay people to help me. So when I'm doing this, it reduces the amount of money I'm spending. And finally, we're working with an industrial partner to scale this up. So these are 3 10,000-liter tanks set up in parallel. They actually have 12 of them, but we have 1 for limestone, 1 for tomato roots, and 1 for CMC. Using this system in 12-hour increments, we're able to treat, or we are hoping to be able to treat 20,000 liters of water per day to recover phosphate from their manure ponds. Thank you very much. I want to thank everyone who has helped us out, along with previous funding agencies. Thank you very much for listening as well.
All right, we now have time for 3 minutes of Q&A from the judges. Take it away, judges.
First, it's unclear how you're going to deploy this in the field and how is water running through it.
So the way that we have it set up is that there's cement well. These cement culverts are built in on farms. They tend to use them for watering holes for cattle. That's actually the first one I showed you. With the ERCA site, they actually installed them for us on purpose. Then we can just drop the filters in, so they're actually removable and you can place them somewhere else again. So that's generally the idea. We want to move them back and forth. You shovel everything in or put the drainage sock in, and then you start pumping water to it.
So how would this work? We live in a region that's one of the most tiled and drained regions in the country.
So you just
We live in a region that's one of the most tiled and drainage tiles.
Oh,
So
yeah.
how is this going to work with, and that's a major phosphorus delivery to the water system. Are you going to intercept those?
It's kind of dependent on the site. So on our first site, it was, they actually set it up very badly when they built the field, but the cow manure was leaking into the water stream that was the cattle were drinking from. So we were pumping water into our filter and back into that system. The ERCA site is an artificial wetland. So what they do there is actually pump water from a stream into the wetland. It passes through our filters before going back into the stream.
Okay, thank you.
Other questions?
I had a similar question, but I still struggling how you scale up what you are talking about to the actual system where if it's a filter, did you do any scale-up studies? Like when you said Bruce Peninsula, you did the study. Is it the same as ERCA site, or?
So the ERCA site, yeah, they are 60 inches in diameter, or 5-ish feet, 6 feet, something like that, in diameter, so they fit well within the cement well. So that Bruce site was a 48-day study, go with water flowing through it. For that system, the ERCA site, I'm setting up on Monday. It'll be ready to go.
More questions?
Tomato roots, what's the expected lifetime?
Yeah, so we're still working on that. There is a decay in the binding capacity as they get older. Regeneration-wise, we've been able to get up to about 10 cycles before we start losing more than likely go down below 80% binding capacity. The other thing we're interested in is their field lifespan, because there's going to be bacteria and stuff on them. What we expect is that because they're already in the ground, surrounded by water all the time anyway, that they should survive fairly well. And these roots that we're using are actually a couple of years old already. So we've started growing our own to do small-scale lab studies to start working on that as well.